Previous videos, we worked on understanding the running time of algorithms by developing functions that would map from the input size of the algorithm to the number of steps that it would take to complete. So the goal now is to categorize those functions using asymptotic analysis. And what we mean by asymptotic analysis is that we're basically going to disregard the behavior of our growth functions for small inputs, and we're going to focus on how those functions grow as the input sizes approaches infinity. And that's how we're going to develop our categories. And we'll eventually provide some mathematical definitions of those categories, but let's start with some informal rules of thumb. So the informal idea is that our functions are going to be categorized according to their dominant or fastest growing term. And what that means is that we're basically going to throw away constants in lower order terms in order to determine the category that we're working with. So let's see some examples. This notation can be read as 10n is in big theta n. So the category is big theta n, and we're saying that 10n is in that category. We could also say that 10n is order n. And how did we end up putting it in that category? Well, as we said here, we're going to throw out constants. We're going to disregard them. So this 10n just becomes n. And that's how that ended up in that category. Let's do another example. So 5n squared plus 2n plus 3. So maybe we worked really hard to analyze some algorithm, and it had a set of five nested loops that each have been done times, and so on. And we ended up with this growth function 5n squared plus 2n plus 3. That's exactly how many steps this algorithm performs. Well, in order to find the category, the big theta category for this algorithm, we're going to throw out the lower order terms. And what I mean by lower order terms are, if your function is composed of a number of different elements added together, those elements are the terms. And the slower growing terms, right, n versus n squared, just get thrown away. Constants thrown away. We're left with 5n squared. And again, we're going to throw out the constant. So the 5n squared just becomes n squared. So my category is n squared. It ends up in this category, big theta n squared. There's one more example, n log n plus n. So here, the lower growing term is this n. And you might be momentarily tempted to throw out the log n, right? If it's n times log n and the log n is slower growing, well, we should throw that out. But that only applies when we're multiplying values together. That only applies to constants. So here, for 5n squared, we threw out the 5. But log n is not a constant. It doesn't get thrown out. So the category is log n. We're in order n log n, or we're in big theta n log n. So that's the rule. Let's take a second to try to figure out why that rule intuitively might make some sense. And to do that, let me show a couple of quick demos. Here we go. Let's compare the function 10n to n squared. Now, if we're just looking at this figure, we might be tempted to prefer n squared as an algorithm. It takes fewer steps for all of the inputs that are being plotted here. And we want faster algorithms. We want algorithms that take fewer steps. But of course, you are smart enough to recognize that if we look a little bit further along the x-axis, if we look at larger inputs, eventually that n squared is going to end up with larger values, being a slower algorithm than 10n. Well, what if we compare n squared to 20n? What if we use a larger constant on our n here? Here, once again, we might say, well, actually, n squared is looking pretty good. It's faster for all of these values of n, so maybe we should prefer n squared. But of course, you know what's going to happen if we look a little bit further out. Eventually, that n squared grows faster. It's going to dominate our 20n, and we're actually going to prefer our 20n algorithm if the input is large enough. And that same story is going to repeat for any value of any constant value that we select to multiply by n. Always going to be the case that eventually, no matter how big that constant is, we're going to prefer the n algorithm, the order n algorithm over n squared. So that's one justification for throwing out the constants. They may change the story. They may change the story in the short term, but they're never going to, in the long term, make a function with an n squared in it better than a function that is linear. Okay, well, I said faster and slower a lot when I was working through that little example. This is the summary. Despite constants, functions from slower growing classes will always be faster eventually. You have to be a little bit careful with this wording. When I'm talking about a slow growing function, I mean a function where the value of the function is growing slowly as the input size increases. So like log n is an extremely slow growing function. Even when n is really, really big, log n doesn't get very big. And what that means is that if an algorithm runs in log n time, it is a fast algorithm. So that's the potential confusion. Just have to keep that clear. Okay, so that's one reason that we might want to drop the constants. It's not going to, yeah, that's one reason we might want to drop the constants. How about lower order terms? Let's look at another example. Here we go. Now we're comparing n squared plus 3n to n squared. And what we can see here is obviously n squared plus 3n is larger. There's this gap between them. And this isn't a case where that gap is going to go away, right? If I look out farther along the x-axis, it's not like eventually n squared will end up larger than n squared plus 3n. That isn't going to happen. N squared plus 3n is always going to be the larger of the two. And as we can see, that gap between them is actually getting bigger, right? If we look over here, 3n is not very big, but as we look further along, 3n has gotten bigger. So the gap between these two functions is going to grow as n increases. So we might be thinking, okay, well, that really sounds like that 3n difference here is important, and just throwing it out would be throwing away some useful information. But let's see what does happen when we look a little bit further out on the x-axis. We were going up to 20 before. Let's multiply that by a factor of 10 and go up to 200. What do we see? Well, now it looks like n squared plus 3n is almost landing right on top of n squared. We can hardly see the difference. So you can tell by a little tiny bit that n squared plus 3n is above. It's a little bit larger. But that difference between them is looking very insignificant. And if we go out a little farther still, let's say we increase n by another factor of 10. Now they're indistinguishable. They look like they're right on top of each other. They look like exactly the same function. Well, how can that be, given that we know that the gap between them is actually growing and growing as we go, as n increases? Well, that's true, but if we consider the two parts of this function, the n squared part and the 3n part, the n squared part is growing so much faster that it's overwhelming this 3n part, right? So once we're up here at 4 million, right, if we look at the y-axis here, we've gotten to 4 million. Well, this 3n is very small in comparison to the overall magnitude of the function. It's getting washed out essentially by this faster growing term. And at this point, it seems like the 3n is kind of an irrelevant detail if what we're interested in is kind of the shape of this function as it grows. It's really not having any impact in the long term. These two functions look exactly the same. And that's the justification for dropping these lower order terms, the informal justification. Okay, one more quick example. You might be thinking, okay, that all makes sense. But why should we drop constants for functions that are in the same category? They're in the same order of growth. So if we compare 10n and n, for example, Clearly 10n is larger. It's always going to be larger. And no matter how far I go out on the x-axis here, that gap is not going to shrink, right? It's not going to disappear with larger values of n. It's always going to be 10 times as large. Well, it's actually true that in practice, it's not that we never care about constant factors, right? If I have an algorithm and I work really hard and I make it 10 times faster, well, I've only increased its speed by a constant factor, but I'm probably going to be pretty happy about that. So I do care about constant factors, but there are some reasons that they're not going to be our priority for analysis. One is, more than the absolute speed of an algorithm, what this asymptotic analysis is about understanding the impact of increasing the input size. So if I have a linear time algorithm or two linear time algorithms, 10n and n, for example, and I ask the question, what happens when I double the input size or when I increase the input size by a factor of 10? In some sense, the answer is the same for both of them. It's going to take 10 times as long or 100 times as long if I increase the input size by 10 or if I increase the input size by 100. So that story about the impact of increasing the input size doesn't change at all as a result of the constant values. So that's one reason that we may not be interested in the constant values. And that's really another side of that same story is what happens if we use a faster computer? So if I get a computer that's 10 times as fast and I'm running a linear algorithm, well, the story of what happens is that I can process 10 times as many inputs, and that constant factor that I might be multiplying by that n value doesn't change that story. So that story is the same if the running time was 10n or 100n or n. Buying a computer that's 10 times as fast will allow me to process 10 times as many elements as I could with my slower computer. If the algorithm was an n squared algorithm, doubling and getting a computer that's twice as fast doesn't allow me to process twice as many elements. So it's a different story in that case. The other reason we might not want to focus on constant factors is that they are influenced by the kinds of distractions that we talked about when we introduced the choice of basic operation. So if we pick a basic operation, that's going to change the constants, even though it isn't really fundamentally changing the way the algorithm operates. Constants could be impacted by programming languages and lots of other sort of irrelevant details. Okay, so let's kind of recap all of these ideas. So our process is that we're going to drop constants in lower order terms, and that's going to give us a set of categories, a set of classes. So let's draw some of those out. For example, log n. We'll say theta log n. That's a category. And in that category, we have things like 10 log n. We have 15 log n plus 12. We have an infinite number of different functions that all, once we apply our dropping constants in lower order terms, end up in this log n category. Similarly, we have a category for n, theta n. And in here, we have things like 12n, we have n plus 26, we have 200n. We have an infinite number of functions, but they're all considered linear functions. They all land in this n category, this theta n category. And all of the functions that we discussed when we did our previous sort of discussion of different function families, we're going to have a category for each of them. So how about n log n? And we have a bunch of members of that family. So, 2 n log n, etc. And we're going to have a category for n squared and a category for n cubed. And a category for 2 to the n. and a category for n factorial. And again, there are an infinite number of these categories, but this is a few of the sort of usual suspects, a few of the cases that are going to come up now and again. And there's no overlap between these categories. A function lands in exactly one category, and they have the property that any function in this category is going to eventually be worse than any function in this category. So it's providing an ordering on all of these growth functions, a categorical ordering. So all of our linear functions are in some sense eventually better, slower growing, than all of our n log n functions. All of our n log n functions are eventually, in the long run at least, better than all of our theta n squared functions. So these categories are ordered in that sense. We can think of this maybe analogously to biology. So in biology, it's very important to categorize life forms. So you have kingdom, phylum, class, order, family, genus, species. So the fundamental, categories of life. Everything is an individual species are categories and categorized into sets of a genus, etc. For computer science, these are our fundamental categories. So I guess we could say that the individual functions, running times for individual algorithms could be considered a species. And then these big theta categories are like a genus, perhaps. And all of the different algorithms in that genus hang together. They're sort of all, in some sense, worse than all of the n log n species and better than all of the log n species. So this is kind of our most fundamental categorization of algorithms and algorithm runtimes in computer science. Notice also that this provides sort of another justification for our flexibility in picking basic operations when we're doing algorithm analysis. So we said when we introduced this notion of a basic operation, it doesn't really matter that much, the exact operation that you pick, as long as it's something that takes a constant amount of time and it happens in the innermost loop. And the reason now we can see that it doesn't really matter what you pick is that any reasonable choice of a basic operation is going to leave you in the same category. So it doesn't really matter what we pick in that sense, because as long as we make a reasonable choice, it's going to be, it'll leave you in that same big theta category. Okay, so this has all been a little hand wavy and informal. What we're going to do as we move forward is we're going to come up with mathematical definitions of these big theta categories and also introduce notions of upper bounds and lower bounds when we introduce big O and big omega notation.